we are responsible, right, as producers of technology for ensuring that we provide the tools to users so that they can make sure that their models are running, right? One thing that we are kind of seeing every day, right, is we expect the models like the ChatGPTs of the world and so on to just understand what we do, right, and just work out of the box. That's not how edge devices work, right? Like it's a lot more complicated. And so with the models, we are putting out tools to actually monitor models in the field to give the tools to engineers to like figure out, how is it behaving, right? Is it working and is it not working? And why is it not working? Because it's never going to work forever. And so we should make sure that people understand that there is work to be done beyond just the creation of the model.
The main value of AI is that it's very easy to customize to the workload of the end user. You can create a device, a industrial sensor, and you can fine tune it or train it to the data of the specific industrial customer you're deploying it to much, much more easily with much less work and expertise than it would take to develop a traditional algorithm to accomplish the same results. And so in fact, it is the ability to develop models that are custom for a task, custom for a product, and custom for an individual customer using that product. Is huge value in AI. And that's, I think, oftentimes lost in the hype about AI.
Really, that's the golden ticket, is data collection from the field, create the model, and then push that model back to where the device is running.
Welcome to Coredump Sessions, the podcast for IoT leaders, firmware engineers, and embedded systems enthusiasts. Each episode, we bring you insights from the leaders and innovators shaping the future of connected devices. We'll talk about what's breaking, what's working, and what it really takes to build reliable products at scale. Let's jump in.
Hi, everyone, and welcome to today's Coredump live session. We're going to talk about building edge AI models that work in the real world. You know, we've been talking a lot about AI, and in large part it's because we get a lot of feedback that you all are interested about the topic, that you're building devices with AI, and that you want to hear from thought leaders or understand what the best practices are. So hopefully today we'll bring some of those answers and certainly ask many more questions. For those of you tuning in live, thank you for being here. One of the benefits of joining live is that you can shape the conversation. Today's session is part of an ongoing series, and every episode is on all major podcast platforms. You can watch or listen to past sessions and subscribe at memfault.com/coredump-sessions. And we'll drop the link in the comments, in the chat. All right, so with that out of the way, let's talk about today's session, building edge AI models that work in the real world. We've got some amazing panelists today, starting with David Tischler. David is a developer advocate at Edge Impulse, helping the community learn about the shifts from the cloud to the edge and how running AI and ML workloads on tiny devices is 100% achievable today. In his spare time, David loves horsepower, drinks way too much coffee, and is an extreme recycler. Welcome to the show, David. We're glad to have you here. I'll have you know I quit caffeine in 2016, but I'm delighted to know some people are still enjoying it.
Way too much caffeine. Now I'm coming to you live from Phoenix, Arizona, and it's 8:03 a.m. So I do have my coffee, but it seems like it's an acceptable time.
Right. And joining us as well from Edge Impulse is Alessandro Grande. Alessandro is a product leader focused on Edge AI, IoT, and embedded system. As Director of Product Management at Edge Impulse, he helps engineering teams build smarter and more efficient ML-powered devices. He previously held management roles at ARM and chaired the 2023 TinyML EMEA Innovation Forum. Welcome, Alessandro. So glad to have you here.
Awesome to be here. Hi, Francois. Hi, everyone. Great to have a chance to talk to everybody today.
As always, my name is François Baldassari. I'm the founder and CEO of Memfault. Memfault builds observability and software updates infrastructure for connected devices manufacturers. I'm also an embedded software engineer who's worked on a number of devices you've heard of. And joining me today is Thomas Sarlandi, our head of products here at Memfault. Thomas is an entrepreneur, device software leader, and tech executive with a long list of achievements. But more importantly, he's someone who talks day to day with a lot of Memfault's customers, and so has a great feeling of where companies are investing today and what the big challenges are that they're focused on. Hi, Thomas. Thank you for joining us from Paris.
Thanks. Excited to be here.
So we're very lucky to have the folks from Edge Impulse here today. I think of Edge Impulse in many ways as the leader in Edge AI infrastructure. But of course, this is today. Edge Impulse has been around for a while, and I think it took real foresight to see how things would develop to the moment of hype than we see today. So maybe Alessandro, you can get us started. How do we get here today? What did you guys see at the time that told you that the moment for Edge AI was coming? And where did you start? And what did you see as the first applications that started emerging?
A great question. I mean, I always like to think about the history of things, right? And I think this is an interesting one. I was at ARM about 5 years ago, and at the time at ARM, we were working on the latest MCUs, a lot of the ones that you see out in the wild today. And a lot of these MCUs had these additional, at the time it was like, people can do AI, can do ML on these models. But really the question was, how are we going to enable people to do this, right? Like the challenge was real. We're putting capabilities in these devices, but reality is nobody from an ML background is actually capable of developing AI for these devices. And so I started looking into that at ARM, and there was a clear gap. There was a clear challenge, right? And the challenge was really around tooling built for non-ML engineers, right? But actually for embedded engineers. And I started collaborating with various partners and eventually found Edge Impulse to be the right way to go, right? And at that point, I decided to join the team and come to work in product at Edge Impulse. And really, I think that the really interesting piece, right, is that back in the day, ML was built by data scientists, ML engineers, AI practitioners of different kinds, and it was all done it was all built for the cloud, right? For these large compute platforms. And the real difference, and we'll get into more details later, but the real difference is about like the fact that world that has no constraints, right? By design, you just don't see any of the constraints that exist in the hardware, right? And so when it comes to embedded, there's a lot of constraints, as we all know, right? And things are just more complex. And so we had to build tools literally to go and serve a different type of hardware. And yeah, we'll get into the details later, but that's really a bit of the history, right? Like it was needed. There was really nothing that could enable engineers to build AI for embedded devices.
It's one of those things that has happened, as often things happen slowly and then all at once. It seems, if you're an outside observer, it seems that AI at the edge happened overnight, that all of a sudden it was everywhere, TinyML and conferences and edge devices. And also, of course, in the broader context of LLMs taking over, the mind space of IT organizations worldwide. But I remember, maybe Thomas will remember also, when we were at Pebble, which was a while ago now, we were pitched MCUs with tensor or with neural acceleration units, like back in 2016, almost 10 years ago. People are thinking about this.
Yeah, and I think at the time nobody, or at least we did not really know what to do with them. We kind of had an idea that you could use them for voice command detection, probably is the thing that was the most relevant to us at Pebble. There was some form of gesture recognition that was already there, but that's kind of what I'd love to hear from you guys, is like, what are the use cases that were popular? Like, I think those use cases were popular back then. Are they still popular today, or what are the most common use cases today?
Yeah, great. I mean, it's always interesting to talk about like actual products, right? And what people are building. I love that. Just one comment on what you mentioned about like, how things started, right? It is true that like voice keyword spotting was really a big thing. And the reason for that, I think, is that there was a lot of large corporations that were building things that we know, right? Like Alexa and, Hey Siri and all that, right? Like that was all being built at the time, and a lot of those things were running on the edge, right? So there was literally a lot of research, a lot of work around enabling devices to detect keywords and commands and things. And then the challenge, the big gap was for anybody else developing these things, right? That's the tooling that was missing. But in terms of like use cases today, I mean, those are still things that work, right? And are still possible to be done, obviously. But I think things are shifting a little bit, right? It's a lot more personal devices, a lot more industrial devices as well. So when I think of personal devices, I think of wearables, right? So I wear 2 wearables every day. I have my Oura Ring, right? That is kind of detecting my sleep and is telling me how well I wake up every morning and how much energy I have. And then I have my Apple Watch, right? And a lot of the stuff that runs on these devices is actually running on the edge itself. There's obviously the use of smartphones as another edge device, right? That can communicate with the end wearable. But really, wearable technology, I think, has evolved a lot, and we're seeing very accurate models now that can detect all sorts of things, right? Like stress levels, oxygen in your blood cycle in women. There's a lot of really kind of interesting applications that have come out in the last few years. And then the other aspect, or the other vertical where I see a lot of innovation, is really around the more boring industrial applications, right? Where you're trying to really optimize for accuracy, really. Like you're trying to figure out whether your machine has produced anything that is faulty or different from what you expect, and really detect that in real time as quickly as possible, right? With a high accuracy. That is something that has evolved a lot, right? We went from like large machines with very big CPUs, right? NVIDIA Jetsons and so on, to now being able to do things like that on a small microcontroller, right? And still have the same level of accuracy and reliability. So really, it's interesting how like the application hasn't really changed. What has changed is the way you implement it and how efficient you can be, both from a cost perspective, but also from a power budget perspective, right?
Yeah.
And so I think that's interesting in that sense.
I was going to ask you about that because I think when we think about edge, there's the question of why do AI at the edge? Why do you want to run it directly on the device? And you just answered, but I think for everyone, maybe it's important to remind why we're trying to do AI at the edge, why you're pushing it as close as possible to the sensor.
There's a catchword in there, though. There's something that needs to be defined. What is the edge? Because Alessandro and I, well, all of Edge Impulse for that matter, have our idea of what the edge is, but it's not the same for everyone. Is it the furthest endpoint, or in the telco world, which I'm not too familiar with exactly how much telco equipment Nordic produces, but they define the edge differently. They define it as the base station typically of a cell phone tower, but that base station of a cell phone tower actually is more like a data center because it has essentially unlimited ping, power, and pipe, which are the 3 things that essentially, allow for the level of compute. So our definition, tends to be that last device, like Alessandro was describing, the watch, the wearable, but there's also this other more nebulous edge, which are like the gateway class devices. And those could be, if you think about the scenario that Alessandro was just describing in the factory setting, right? Those are like essentially on a manufacturing line, on a production facility. If you have widgets or things coming down the line, the assembly line, or even like an automotive factory or something like that, you've got a workstation class device with a camera, and that gives you an incredible amount of power. You have, you have Ethernet, you have possibly something with a GPU in it. So, you kind of have to define or understand your use case very specifically. The use case of the smartwatch or a ring or a tracker, some sort of wearable, that you're going to be talking about an MCU class device that will survive on battery power for a long amount of time. But then over at that factory location, I mean, that's something that's just plugged into mains at all times. You really don't worry too much about that.
I like to think of the definition of the edge as any computer that has sensors or actuators attached, whose main purpose is interacting with those sensors and actuators. So if you think about like a server, of course, server has sensors and actuators. It has a fan and it has temperature sensors, but the main purpose is computation, right? Like, whereas you think about a sensor in a factory, like sensing and reacting on the sensor input is the main purpose of the device. Because if you say only devices outside of data centers, then of course you have edge devices that are here for data center management, like HVAC systems. And if you say only devices that don't run x86, well, ARM is starting to enter everywhere. And if you only talk about the furthest edge, the smallest devices or battery powered devices, I think you miss these camera use cases that are so, in my opinion, are the place where we have found the best product market fit for edge AI applications today, right? It's audio and video are by far as I've seen so far, the places where we've gotten the most maturity and the most actual deployed models out there. And maybe Alessandro, you have some other examples.
Yeah, I would agree with that. I think it all boils down to like what is the value for the user, right? Like I think when we started, we thought that there was two killer applications, right? Like when we set off to like build Edge Impulse, we thought it was all about keyword spotting, right? Because everybody was trying to do that at the time. And it was all going to be about predictive maintenance, right? Reality is keyword spotting. I mean, yes, it's interesting, right? But actually it's very boring, right? I mean, you need it, but it's not really what's going to drive value, right, to the user. It's kind of it's a tool you need, right? But it's not really the end result. It's
like
a component.
plug-in.
Exactly. And in case of predictive maintenance, the challenge there is that you might save some money in 10 years' time, right? But you're not actually getting any value today, or at least you don't know whether you're getting any value or not, right? There's no guarantees. And so you're trusting someone to give you value in a few years down the line. And the problem there is that companies are not willing to invest, right? Because there isn't really a return on investment that is clear from the get-go. And so to your point, video analytics, right, is super valuable because you can get outcomes right away, right? Like you can stop things from being produced. You can push them down the production line. You can stop a car from entering a parking lot. You can kind of stop a person from entering your office, right? Like there's a lot of things that you can do that potentially can add value or reduce risks, right? And kind of potentially cost you less, right? And so I think video is really an image analytics in general is really a big one, especially for industrial, right? Not so much for commercial. I mean, I would say in commercial, right? In consumer, sorry, not commercial, in consumer space, drones probably is the closest to that, right? Where you can see
On white balancing, there's nowadays AI algorithm for cameras, right? I think all of our iPhones and all of our SLRs nowadays have some little models that are used to do image extrapolation, hyper resolution, even potentially implementing specific blur or things like that are done with little neural nets. So it's really image processing is huge.
Yeah, I think that raises an interesting point around like the kind of difference between models that are built for a specific use case, right? Like auto white balancing is an interesting one where you probably don't need to build a model every time you build a camera, right? Like there's probably models out there that you can use out of the box, right? Versus like you're trying to detect a specific object you're creating in your factory that nobody else creates, right? It's your object, you're creating it, in which case you might have to build a model custom for that device, right? For that factory floor, right? And so I'd like to kind of differentiate between those two types of models, right? Because actually there is cases in which you can just get an off-the-shelf model and it will work out of the box. But in a lot of production cases, right, you're looking to, at least if nothing else, you're looking to fine-tune, right, your model for a specific use case. And that's where, tools like Edge Impulse and others come into play to kind of customize these models and build them for your specific use case. So I think, I think there's these kind of two classes of use cases, right, that are interesting to keep in mind as well.
Alessandro, bring up a point that, in my opinion, is crucial here, which is that we think of AI as enabling new use cases in terms of things that traditional algorithms couldn't do. If you think about auto white balancing or things like that. But actually, that is not the main value of AI, in my view. The main value of AI is that it's very easy to customize to the workloads of the end user, right? You can create a device, an industrial sensor, and you can fine tune it or train it to the data of the specific industrial customer you're deploying it to much, much more easily with much less work and expertise than it would take to develop a traditional algorithm and doing like data science, hands-on data science, develop a traditional algorithm to accomplish the same results. And so in fact, it is the ability to develop models that are custom for a task, custom for a product, and custom for an individual customer using that product. And the fact that they can, you can basically just feed them the data and let them train themselves. I mean, that's an overstatement, but for the sake of the conversation, is huge value in AI because it unlocks new use cases, not because traditional algorithmic couldn't get there, but it couldn't get there that cheaply, right? And that's, I think, oftentimes lost in the hype about AI. It's this customizability, fine-tuning is so powerful for things like sensor data analysis.
Yeah, I 100% agree. I think what's interesting is that the real value is in that customization, right? Because I always think, and I always tell our customers and developers that if you can find a way, right, and if you can find an algorithm that can do whatever you're trying to do, right, in a, let's call it, classic way, without having to train anything, do that, right? That's going to be much more efficient. If that works, right, you're done. There's no work to be done, right? And that in a lot of cases can be a lot more efficient than trying to train a big model, right? Because when you train a model, effectively you're trying to simulate the world, but you don't really know what the laws of the universe or the laws of physics are, right? So you're trying to basically come up with those laws within the model itself, right? But actually, if you can know what the actual rules are, you can just write the code for those rules, and you get the right result out of it, right? So for example, even in Edge Impulse, right, we use a lot of DSP techniques, right, for different type of sensor processing, and that is because actually in a lot of cases it makes way more sense to do things like that in a simpler way than trying to let the model do everything, right?
Well,
that actually is
the secret of AI, in my opinion, Alessandro, which is that oftentimes the pre-processing matters just as much as the model. And the pre-processing is traditional DSP methods. And oftentimes when you ask an ML engineer, why did you take this image and compute the histogram of motion vectors across the image? Why is that what you're feeding your AI model? And they say, well, we found that that's what works, right? That's what you hear, is it's empirically determined to be reasonable of an approach. And so we think of these AI models as you feed them the image and it does all the work. But actually, to your point, we do quite a bit of DSP work, and implementing AI at the edge still requires expertise, not so much in the training of the model. That's well handled by things like Edge Impulse, but in prepping and massaging the data to get it to a point where it can effectively be leveraged by a model.
But that's one thing that I really like about Edge Impulse is when you look at the developer documentation and you look into the tool and what it does, it feels to me, and I want to get confirmation from you guys, but it feels to me like a big part of the product is helping embedded engineers come up with ways to first extract data from devices and push it to a developer desktop where you're going to be doing work deciding which features you want to use, giving you a lot of ideas of what features you can use. And then once you've decided what feature work best and what feature you want to use, you make it very easy to implement the feature on the device. But suddenly when you say that, you've already broken we're going to train model at the edge. You've broken that down into something much simpler, basic blocks that I can understand without being an AI ML engineer. Is that accurate?
Yeah, I would say maybe one thing to keep in mind, right, is that we named Edge Impulse and we talk about impulses that we generate, right? Because actually we're trying to find a name for the ML pipeline, right? We were trying to find a name for actually DSP plus a model, right? I think it's interesting, right, that you bring this up, because for us from day one, right, we've always thought of a pipeline, right? And you want to do pre-processing, and then you want to do an ML model. You want to feed that into the ML model. And we enable users to do the pre-processing and figure out which pre-processing to use outside of Edge Impulse and then import it in Edge Impulse. Or we also allow users to use our tools to actually do some of that search, right? We have tools that allow experiment tracking, right, in the context of ML models, but for also DSP, right? So we allow the users to kind of look for the best combination of DSP or pre-processing of different types. and the ML model, right? And so actually, we believe that the right approach, right, is not to separate these two things out and try to optimize only one or the other, right? But actually try to optimize for both, right? Because actually that's where the real value is, right? Is trying to find the best pipeline, the best impulse for your use case, right? And so yeah, we allow users to do it outside of Edge Impulse or inside of Edge Impulse. We're very flexible. We try to keep everything as open as possible in that sense.
Before we so go ahead, David.
I was going to say just real quickly, Francois. I think one of the key words that we tend to focus on is democratization, because Thomas, you were, describing that you're not necessarily a machine learning engineer or a subject matter expert in data science, right? But along with that experimentation that Alessandro is describing, you can absolutely build an impulse or a pipeline and explore your data set and understand what the features extracted are going to do. And you can come away with a working model, quite honestly, a very accurate, highly functional model that you can then take and implement. And you can always, go back and iterate and fine tune. An ML model is only as good as the data that went into the model, of course, which is a whole different discussion around data set curation. We can actually probably touch on that later when it comes to the deployment side and the ML ops loop. But I think that keyword democratization is one that we focus a lot on to make it easy using the Edge Impulse platform to come away with an AI model that's functional.
And I think that's where
something you said, which is you were asking why are the models being pushed at the edge. Do you want to pick up that thread, Thomas, and tell us a little bit about your thoughts on that? And then I'd like to move on to how we actually build those models, the hardware, those AI devices.
Yeah, I mean, I think it's obvious to the four of us, but I don't know if it's completely obvious to people from the software engineering world. I think I think the reason is that because we have a lot of devices that are not always connected, and so they can't just stream data back to the web or back to the data center. We have a lot of devices that are running on battery. Even if they have the network can be expensive or can be very limited. And then at some point, by pushing the computation at the edge, you're just reducing your cloud operating costs because you're just getting the device to do a lot of the pre-processing, and that way you've pushed the work at the edge. I think that's especially true in all those videos example where you also get into privacy reason. Like if you can run a model at the edge, then you've avoided uploading the image and you're able to just send the signal that, hey, an animal was detected or a person was detected, and then the user can decide to look at the image, but you're not streaming continuously the video feed back to the web. So these to me are the most common reason, but I think it was
so latency, I think super.
Yeah.
Right?
Yeah, on some application like robotics and automotive. Yeah.
Self-driving vehicles. Absolutely.
Exactly.
There's no
self-driving vehicles. You
time
the
to
car.
send.
You don't want to wait for the cloud to tell you,
That there's
That
a
might-
bike in
yeah.
front of the car.
Yeah, and the reliability, right, of all that, because if the connection to the cloud, stops to work, you don't want the brake to not, to stop to work as well, right?
Yeah.
And the other one that we mentioned earlier is battery, right? If you're running off battery, like wearables, right, are good examples. I'm still upset that I have to charge my watch, right, almost every day. It's annoying, right? I wish I could do it less. I mean, my Oura Ring I can charge once a week, right? So that's already better. But yeah, I mean, I think there's still some work to be done there.
Summarizing, it's battery, bandwidth, intermittent connectivity, latency, privacy. Those are our reasons to deploy ML at the edge. And it doesn't mean that every application will warrant it, but certainly some will. Let's talk about how we build these devices and maybe first how we build the software. David, I feel like this is probably your wheelhouse. When I was building devices that were AI powered, especially at Oculus, this was a very complicated process. We had AI engineers and data scientists who use MATLAB to develop the models, right? And then eventually that would be passed on to C++ performance engineers who would transcribe that into C, and then would be deployed on the device, and the systems engineers would manage the system. That was the state of the art. I would say in 2017, 2018 for deploying a model and training a model and data pipeline management. What does the software look like today? If I were an embedded software engineer, I know nothing about AI, but I want to investigate those techniques. What is the MVP software stack to get a model running, to kind of plug some data into a model and get it running at the edge?
Yeah, that's a good question. You're opening a whole different can of worms that we'll have to save
Yeah.
for another session, which is prototype to production, because there's only 28 minutes left, and that's not going to be enough to cover that one. The prototype to production conversation is an entire episode in and of itself. But you're really not too far off in your overall theory there, which is, what was the scenario? Oculus? Yeah, you have some machine learning engineers, DSP engineers. Okay, fine, they're using MATLAB. They're going to toss it over the wall to the embedded folks, C++ folks, and they're going to get it to run on the given hardware. And then eventually that goes further down the chain to productization. And, in Oculus, of course, there's the, what is the fit and form factor and the mold, and then what PCB is in it. That's going to drive a lot of what hardware is inside of it is also going to drive a lot of the design decisions back up the stream from the DSP guys and the engineers and also the embedded folks. And then eventually it goes out to distribution shipping, and there's a product in a consumer's hand. I would say, specifically to your question, which was, what does an embedded engineer who is just getting started, what does that look like? I mean, that's honestly probably the perfect scenario for Edge Impulse, because you're talking about someone who is firmware, a C++ engineer that really truly is not a subject matter expert in machine learning. That's a different skill set. So that's where someone who is an embedded engineer would come to Edge Impulse and quickly get started with curating data into a data set, building their pipeline, and coming away with a functional model that they can deploy onto development hardware. And I'm saying development hardware very specifically, because that engineer is going to have on their desk something like a Thingy 53 or the Nordic Developer Kit, or a simple thing like a Raspberry Pi Pico, or some other, or an Arduino, any of the Arduino range. Something
that model, what is it actually? Do I just get a Python blob? Do I get some C code? And how do I get it on my device? Do I have to flash a specific firmware? Let's say that I have a custom firmware already. How much work is it to get that all together?
Alessandro, how many options do we put out these days, depending on how many boards are supported versus just the raw libraries? And I mean, there's Docker containers, there's TensorFlow. Give me the overview, Alessandro. How many options do we have?
We have quite a few, but I think it boils down to, like, actually, it's interesting, right? It kind of boils down to that, what you were saying, David, about like that interaction between different engineers, right? Like, I think depending on who you're working with, right? Like which engineer of which department, right? Like they might have a different expectation of what kind of deployment they might look for, right? If you're working with someone that is used to like working with cloud models, right? Like they might expect a Docker container. They're most likely going to expect something that looks very similar to that. In the embedded world, right? You expect something to be C++, right? And that's what we see most commonly used. And so we kind of have these two extremes, right? Cloud kind of, well, not just cloud, but like, more kind of Linux deployments, right? That have like that are Dockerized or
Basically, TensorFlow, full-on TensorFlow, Python.
Yeah, behind the scenes, that's a good point, actually. Behind the scenes, it's all, at least for us, Edge Impulse, right? In terms of deployment, it's all TensorFlow. That's the runtime that we use. We do support, I mean, there's a lot of different ways to kind of generate the model, right? So you could use PyTorch, you could use TensorFlow, right? We support all of that. And there's a lot of developers using, different ways to kind of build models. But in terms of output, we use TensorFlow right now as the kind of main output there.
Yeah.
And runtime.
In terms of hardware, say I'm building a device, I think I may want to deploy to leverage AI either in my product or in the future as an update. What hardware do I need? Is there Can I deploy those models on any kind of device? As long as I have a ARM Cortex-M, I'm good to go. How do you size the hardware for a given AI application?
Yeah, I mean, this is another interesting one, right? Like, I like to think of kind of the developer journey, right? I think beyond our tool, right? I think it's a fair question, right? Like you're having to basically find a compromise between a very performant model and something that can fit on your device, right? And actually, in some cases, you might even have options in terms of what device to use, right? So there's a lot of variables here, and really, you have to like search, right, for all the different combinations, right? And so depending on what you're building for, right, like if you are constrained, what we see often is someone starts with a specific device, right? So you're working for Oculus, right? As you mentioned earlier, you were working for a company that is building a product. There is already a product that's being built now, right?
Yes,
and so you
already have selected a chip.
Exactly. So you already have to fit.
Software was developed.
Exactly. No choice there, right? So you have to build something that can fit on that chip. What we then see is the next you might then kind of, depending on what you're building, you might inform the next generation of chip, right? Like you might inform what goes into the next chip because you might see that there's some limitations with the current chip, right? But staying with the kind of initial deployment, right? Usually you have a target, right, that you're selecting. And then you have choices around how general is the model, right, that I'm trying to build. In a lot of cases, you might start with a generic use case, right? I'm trying to detect any object that passes in front of this camera, right? And then you realize, actually, right, I don't need to do that. That's not, yes, that might be great, right? It might save me from additional work in the future. But actually, right now, I just care about, is there a mouse, right, or a keyboard in front of my camera, yes or no, right? That's the only thing I care about. So I can actually fine-tune the model, right? Maybe that was trained on a larger data set to just recognize these two objects, right? A lot of times, like,
why is that? You're saying you can distill a model down to something that will work for your hardware.
Exactly. So, in a lot of cases, really, it's all about like constraining the problem beyond the model. I mean, this is just problem solving 101. Right? You usually start with a very big problem, and then it's all about like, okay, how can we make this problem smaller so that we're in a place where we can solve it without requiring too many resources, right? As many resources. And then it comes to like actually kind of trying different options, right, and finding the best option for your device. And we tend to use simulators, right, behind the scenes to simulate different hardware so that you can get a sense of like how will this run on this specific hardware, how much RAM will it use, right, like how much overhead will this have, and all that it's interesting also because again, going back to the constraint, right? It's something that an AI engineer, a data scientist will not think about. Like they won't think about the fact that your model needs to be, it needs to fit in like, maybe 100K of RAM, right?
Yeah,
exactly. For us, it's normal, right? And so how do you communicate, right, to your perhaps like data scientists in your team, right, that actually you need to ensure that your model will fit into this, right? A lot of times, like with tools like Edge Impulse, you can run these models, right? Maybe different experiments, right? So different types of models, and then get the output of these models and see what is the actual size. And you can actually see whether it fits on your target, right? So we try to like match effectively the simulator performance, right, or the simulator outputs with actually what the user has actually requested for, right? So I want my model to fit on this ARM Cortex-M device or this NVIDIA Jetson device, right, or whatever it might be, and then I let the team, kind of do all the research they need, and they know that they have this constraint, right? It's built into the tool, and so they can always compare back, and they can always kind of validate that their model that they're trying, the model that is best performing, actually can perform on this device, right? And so it's kind of trying to connect these two worlds.
How do you feel about and we're going to move on to observability for a second.
I want to stay on the hardware for one more second.
I have one more hardware question, but go for it, Thomas, also.
And so I get the feeling that, on the lower devices, we've taken what used to be just a DSP coprocessor or DSP units inside the MCUs, and we've renamed them to AI core into some at some point in 2020 or 2022, I don't know. On the bigger end of the spectrum, if you look at the NVIDIA Jetson and stuff like that, I also get the feeling that we've taken GPUs and we've renamed them to AI core at the same period. So I'm really curious to hear from you guys who work with a lot of real hardware and projects. what are those AI cores that we hear about? How are they different from just DSP or GPUs? And what should an embedded engineer know about them when selecting hardware?
I'll add to Thomas' question because it's exactly where I was going. Like Nordic, for example, acquired Atlazo, which is an NPU AI IP for MCUs. We know that many other MCU vendors are rolling out their custom NPUs. And I'm trying to figure out, are these even helpful? Do we think they're going to converge on a spec or not going to be used at all? Are they already being used? I think similar direction as Thomas was going. What are they? How are they being used? Are they actually the future or are they just a weird experiment?
I'll start with a maybe high level, response, and then David, I'm sure, knows more about the kind of the details of the hardware. But at a high level, I always think of these devices as systems, right? I think we tend to like look at them as like separate components, right, of a system, perhaps like the MCU, the accelerator. But actually, it only works if you can ensure that the whole system is working correctly, right? So in a lot of cases, for example, your accelerator of whatever type is not able to like run certain operators, right? And you need to make sure that it can fall back to the CPU and it can run that efficiently, right? And also, you need to ensure that the coding, right? Like someone coding a certain application, a certain model, right? And writing app logic around it can take advantage of these cores, right? And the system itself actually in an efficient way, right? Because the biggest challenge really is on one end, right? Accelerators that are kind of standalone, right? That then are unreliable because you don't know whether the accelerator is gonna be able to perform whatever it needs to perform, and whether it can fall back to something else. And on the other spectrum, if you have a system that the engineer cannot build an application for in an easy way, then really it's the same problem, right? Like you can't take advantage of the system.
That's why NVIDIA is so powerful. Is CUDA has become such a well-known and useful and documented, etc., interface to build these applications, and that's a huge advantage. The software piece is really critical.
Yeah, it's all about like taking advantage of the hardware you have at hand, right? And I think I'll just add to that last bit, right? Like you need to take advantage of the hardware without you kind of having to do that manually, right? Like as a developer, you should just
in that.
Yeah, exactly. Because you don't like the last thing you want is for someone to like have to spend their time, right? Instead of building an application, to spend their time on how to accelerate the application, right? That should just happen. And I like to think that we can help with that, or we help developers with that. But I'm curious to hear David's thoughts on hardware specifications.
Yeah, I have a couple of different thoughts that are all over the place. So let's see if I can wrangle these ideas. But you know what? The very first and foremost thing, staying at the high level like you are, Alessandro, is this. You need to think about the use case and what are you sensing? What is your application actually doing? If it's something to do with the environment as I'm looking out the window and the temperature and humidity, or a door, whether it's open or closed, does it really matter if your inference occurred in 5 milliseconds, 50 milliseconds, 500 milliseconds? It doesn't really matter. It's a moot point. So, now, of course, there are different scenarios, different use cases where every millisecond does count. We talked about the self-driving car example and applying the brakes if a pedestrian steps out into the road. Okay, yeah, in that scenario, more compute or, faster inference truly does make a difference. So the very first thing is to evaluate what are you doing and does it even matter? If you're running on a CPU core versus an NPU core, depending upon the use case, might not make a difference. Just save the couple of cents on your BOM cost and run it on the Cortex-M. The second thing is what you touched on, Francois, which is the software ecosystem to go along with it. There are probably 100, if not more, discrete different IPs out there. Every silicon vendor is now, like you said, incorporating some sort of an NPU. TI has theirs, Renesas has theirs, Nordic has theirs. Then there's the discrete ones like Halo or Accelera, a couple others out there, DeepX, a few more. And again, it's going to come down to how easy it is to use the SDK, right? Because if you have the fastest NPU there is, and you can get your inference time down to however many milliseconds or at the other end of the spec, frames per second. If you can't figure out how to use the SDK, does it even matter? Because you're going to waste all of your time in development and engineering, and you're better off just going with one that you can make easy use of. So, there's a couple of different things to evaluate there, but I don't know. I'm not necessarily of the opinion that just the performance numbers alone tell the whole story. I think there's more to it than that.
And
That's
just
very
maybe,
clear. Go ahead, Alessandro.
sorry, Francois, I was just going to add one thing. I think if we think about like use cases like the ones we've discussed already, right? Like kind of very discrete use cases, right? You're trying to detect an object, you're trying to detect a keyword or things like that. I think this is all true. I think when things change is actually when you start introducing Gen AI models, right? Running on the edge. In that case, you're actually not able to run them, right? Unless you have beefy.
Yeah, but you're not gonna run one of those on a NP.
Well,
Yes, you are. Not on a Cortex M, not an
No,
M, not an M.
But they're like, I was mostly talking about the MCU vendors, the ones we all know well, who are putting little NPUs. Like that's not going to help you for an LLM. But you're right that there are edge solutions there too. In the interest of time, let's move briefly and talk about observability. That's of course our area of expertise. Thomas, one of the things that we've hypothesized early on at Memfault, looking at this AI, change or this AI technology on the rise, is that these models being, for all intents and purposes, not completely deterministic, would require more monitoring, right? Like we'd have to keep an eye on them to make sure they're doing what we expect them to do. So I guess my questions for you, Thomas, are you actually seeing this in the companies you're talking to? Do they have that concern? And how do they think about monitoring those LLMs? Are they looking at inputs and outputs carefully? Are they just looking at errors reported by end users? Are they using observability data to tune and refresh the models? How sophisticated are we getting there? And where do you think we're headed?
Yeah. So I think I was reflecting, on examples of customers that have been deploying models, and the examples that we see are, what we discussed today. It's voice command, it's activity gesture recognition. That's the lower end, and then on the higher end, we have a number of customers doing some image processing, video processing, and extracting events from video feeds for robotics or security application. And I think the first thing we see is especially on embedded, where you have limited memory, the system can be under quite a bit of stress when you're running those things continuously over a period of time. We just see crashes, and those crashes, they're not unlike other crashes that we already track with Memfault. It's just like the system crashed. You want to know that it crashed. You want to know what it was doing. And probably it's a bug in the runtime that's running the model. That's not really a problem in the model itself, but still good to know that it's happening so that you can work on fixing it. And I think the challenge here is that there's so much RAM that would be useful to replicate the entire model that most people cannot afford to upload that every time. And so that's one conversation, and we have some solutions for that. But then the rest of the interesting questions are what happened when we run the model. And I think the first thing people want to know is how often do we use these models? So we see that a lot, is how many times did we provide an input, and then counting how often different response appeared. So if you're doing some classification, just tracking the output of the classification as a metric measurement is really helpful, because when you do a software update, you can make sure that the distribution of those classification has not drastically changed, which would be a sign that there's probably a bug somewhere, because you're either fixing a bug or you just introduced one. So that's something that we see. And these are the things that we have seen so far. I don't think I've seen anything much more complicated. Like you were talking about FPS, David, like I think I've seen FPS a little bit, like some people tracking how long it takes to process one frame so that they can make sure that they do all the processing in enough time to continue to run in real time, but nothing too crazy. Which
generally,
Good.
like measuring latency across all ML applications feels like a really important data point to collect out of the box.
That observability that you're describing, Thomas, is critical, though, because exactly what you just described, if you push an OTA and all of a sudden your model is no longer working for whatever reason, I mean, the model itself may have become corrupted or flawed in some way, or more likely, if it's, just a derivative of the model that you already had, probably your application code is where the bug lies. But in any case, you need to be able to push a new OTA with a fix. And you need to understand that there was an issue on the device, and that device could be anywhere in the world. And once you understand, oh, wow, there is a problem, you need to also be able to push the fix to that problem. Again, that does not mean travel to every device in a deployed fleet. That's
where we get into the productionized
yes.
AI/ML at the edge, and where you need
yes
both the observability, but as you said, OTA is the number one requirement.
But the speed of iteration changes, right? When you have AI in your products, you likely need to plan to do updates monthly, quarterly, certainly regularly. And that requires a feedback loop, collecting data, pushing updates. That's for me, that's a very, very clearly something that you should consider. It's not just about building the model, it's about figuring out how you're going.
So it's critical for another reason that I see very, very often, which is that if I built a model on my desk, it works wonderfully. However, when I go and push that model to a device in the world, the lighting conditions are different. The camera attached to the device is different. And the environmental surroundings are different. And the model no longer performs as it did on my desk. And I need to be able to push, or actually what I really need to be able to do is to collect data that is representative of the real world condition, because the data that was collected on my desk is not representative of what I'm going to see in the field. And so to build a more robust model, I actually want to collect data from the end point where it's going to be physically located, from that true device, bring that data back to my data set, do whatever curation is necessary, and then build the model based on that. That's how I want to train. And then I have a more robust model. Okay, great. But how do I get that model back to the endpoint again? OTA. So really, that's the golden ticket, is data collection from the field, create the model, and then push that model back to where the device is running. That's a whole episode right there.
We have 5 minutes. Let's use them for a few questions. First from Andy Henson asks, where do you already see fine-tuned edge models outperforming more classical data science and algorithms? I'll start with one. I've seen like eye tracking applications and advanced heart rate monitor based, like PPG sensor data processing to find, health data, derive health data from it. Those are two applications today where the ML algorithms have won unambiguously. We use 100% of the products that are in the field today use ML to implement those. But I'm sure, Alessandro, you have 100 better answers, and maybe Thomas, you've seen a few too.
Yeah, I mean, a couple of I can think of. One is keyword spotting or command detection. I mean, every day we use the typical, hey Siri, hello Google, right? And it always picks up your command, right? Like no matter where you are, how noisy the room is, right? It just works. And that's not something you can do with just pure DSP, right? Or pure...
Trains on your voice.
Exactly. It trains on your voice. It trains on like specific keywords, right? It's kind of trained on a lot of voices actually, right? And a lot of languages and so on. So that's one. And the other one that comes to mind actually is kind of related to yours, but it's actually eye tracking. I was actually really, really impressed by, there's a lot of tools nowadays that have the ability to, like, if you do a video, you can kind of change the video or kind of do post-processing on the video to like put the gaze, right? Like fix the gaze on the camera. I mean, it's impressive, right? It just works, and it's really unbelievable. And that's something again, you cannot do with just classical classical methods, right? So those are two that come to mind. Francois, I just wanted to mention one quick thing, right, on the observability, just because I think it's key. I'm very passionate about this. We are responsible, right, as producers of technology, we're responsible for ensuring that we provide the tools to users so that they can make sure that their models are running, right? Because I think one thing that we are kind of seeing every day, right, is that we expect the models like the ChatGPTs of the world and so on to just understand what we do, right, and just work out of the box. That's not how edge devices work, right? Like it's a lot more complicated. And so with the models, we are putting out tools, and I'm hoping everybody else that's doing similar things is putting out tools to actually monitor models in the field, to give the tools to engineers to like figure out how is it behaving, right? Is it working, and is it not working, and why is it not working? I think it's key, right? Because it's never going to work forever, right? And so we should make sure that people understand that there is work to be done beyond just the creation of the model. I just wanted to say this because I think it's very important to keep in mind.
And briefly from Jean-Paul, what's the relationship between TinyML and Edge Impulse? I think, David, you were writing the answer, so maybe you've been thinking about it. Like what's the difference between those two?
Actually, I was going to tell John Paul to just ping us and reach out to us, but I think we might have actually covered it along the way throughout the duration of the convo. I think that TinyML, or sometimes now known as Edge AI, is more of the principle or this field of running small models on edge devices. Now that's very different than big ML running in data centers on the giant NVIDIA GPUs, like the stuff that is powering ChatGPT and the likes, Claude and the others out there. Of course, the training, that's a whole different scenario. I view TinyML more as the inference that's running on, Cortex and things like that. It's more of I don't know, I guess like the practice of running these kinds of models like this. Edge Impulse being a platform, Edge Impulse being a platform to then help build those models.
And I think, TinyML is maybe the foundation, and it's the industry body and a player in this ecosystem with a specific stack.
Yeah.
And with that, we're at time. It always blows by. We'll always have more to talk about. Perhaps we'll have a follow-up on productionizing, deploying at scale. But thank you so much, Alessandro, David, Thomas, for joining me today. I really enjoyed the conversation. Thank you to the audience for your questions and your comments. And in the meantime, I hope everyone has an amazing week.
Thank you.
Thank you all.
Thank you all. Thank you so much for having us.
Yep, appreciate it. Bye.
Thanks for tuning in to this Coredump session. If you enjoyed the conversation and want to dig deeper, check out more episodes available wherever you get your podcasts, on YouTube, or at memfault.com/webinars. If you have any questions for our team, drop us a line at team@memfault.com. Until then, keep shipping. See you next time.